if you would please join me on page 8 for problem number 74. And again, we had enough students asking for this even though it wasn't on the list. I'm going to go through it quickly. All right, we have a situation here where Robin Hood grabs onto a rope that goes over a beam, and it's a frictionless beam because we're in magic physics land. And he's going to let go of or untie it and release it from the wall, and then it's going to pull him up. So I'm going to go through the setup and I'm going to talk about it. First, this, just like what's going to be on the exam, has multiple free body diagrams, and they are attached to one another. So we're going to go ahead and start off by drawing out Robin Hood. So Robin Hood, here's a beautiful picture of Robin Hood, and then Robin Hood is going to actually have a couple of forces on him. First, we went through how to draw force diagrams last year. Everybody knows the first thing, unless you're in deep, deep space, you can always draw, is the force of gravity. In this case, it's easy because we're on Earth, so the force of gravity is just mg. Now, remember that you never just write gravity. If you just write the term gravity on an IB exam, you will get marked down on it. You can write weight, you can write force of gravity, or mass times gravity. But never just write gravity by itself, because gravity is this idea. But this is a force, and force is mass times gravity, weight of gravity. The other force that's acting on Robin Hood, first, let's ask, is it going to be bigger or smaller than gravity? So we draw an appropriate diagram. What's going to happen to Robin Hood when this all breaks loose? The hope is that he accelerates up, which means what's going to happen? The tension should be bigger. If it's not bigger, Robin Hood's got a bigger problem, he's doomed. So the tension there is a little bit longer. I don't know how much bigger. We're going to solve for that in a little bit. But I'm going to draw it a little bit bigger, and I'm going to put tension. Now comes to the next part. After a free body diagram, after you have the diagram written, I always said I want you to explicitly pick directions. We're going to get to that after I draw the second one, because I want to talk about what we do or how we handle a setup when we actually have a series of things connected to one another. So really quickly, we're going to go ahead and move to the other object. The other object was a chandelier. Just like Robin Hood, we can go ahead and start by actually drawing mass times gravity of the chandelier. It's not the same mass, so I'm going to actually write this as mass 2. That could get us into trouble unless it said it was the same mass. Now we expect the chandelier actually to accelerate Robin Hood up because the chandelier is going to move down, which means the tension on this should be shorter than the initial. When we draw this out, we want these to be able to be fairly close together. The general rule of thumb, when I use to grade a free body diagram, which is not on this exam, the general rule of thumb is I should be able to actually take an eraser, a standard eraser, and cover that center point, and they all should meet there. That's what I use. IB does allow you to draw actually forces where they exist on an object. I prefer this, which is a fairly standard free body diagram. Now let's talk about direction. Direction here is a little bit weird. The reason is, if we look at the system where we have our famous Robin Hood and we have the chandelier, up and down don't really matter because we're actually accelerating in this direction, which is a little unique. Robin Hood's going up and the chandelier is going down. There's a couple of ways we could handle these two different directions. We could say everything is positive in the up direction, but then that would mean when we set up the equation over here, what would actually end up being in the negative direction? Acceleration, and we would actually have to write in negative acceleration. Otherwise, we're actually going to end up with a solution that does not make sense. Instead of doing this, I actually prefer to go back and looking at this right here, what my goal is to make everything consistent with that, which means I'm going to make this direction positive and negative over here, and I'm actually going to switch directions on this. That means both of these objects will accelerate in their frame of reference in the positive direction. So this right here is the positive direction for the system. So again, we switch the directions. Now this is all going to come out and make things nice when we actually set up our series of equations. Let's go ahead and do that. I'm going to switch to blue for this guy over here, just to keep us to where we have some color coding. Now, we end up using the most powerful thing in physics and the most worthless thing. I said this last year. The sum of the forces. The reason it's the most worthless is because we actually don't use this. We use what does it mean? And it means we add all the forces in this direction together. And in this direction, we have T, tension in the positive direction, and we have mg plus a negative mg, because it's in the negative direction. This then doesn't matter, because what we actually were going for was T minus mg. That is what sum of the forces is. And we know that those forces are equal to mass times acceleration.
Why do we know that?
The sum of the forces, Ashley, is always equal to mass times acceleration. This is Newton's second law. We can do this exact same thing with the chandelier. The sum of the forces, again, this here is worthless because what it means is we take all the forces and add them together. I said that the direction here, the down was positive, so we're going to have an m of the chandelier times gravity minus T is equal to the mass of the chandelier times acceleration. Again, sum of all forces equals mass times acceleration. Again, the sum of the forces disappears over here. The sum of the forces actually disappears over here, leaving us two equations and two unknowns. The unknowns are tension and acceleration. And if we look here, we're actually solving for both. Most of the time, however, we only care about acceleration, which means something funny that pops up, we don't want to replace acceleration. What do we want to get rid of? We actually want to get rid of tension. So I'm going to do that in blue. I'm going to actually solve for what is the tension on Robin Hood. To do that, I'm going to add the mass of Robin Hood to gravity to both sides. I'm going to get a new equation, actually a rearranged equation, that says the tension of Robin Hood is equal to mass times acceleration of Robin Hood plus mass times gravity of Robin Hood. This is the same thing as tension. Right, we can replace tension in the second equation. Mass of the chandelier times gravity minus ma plus mg from our Robin Hood part equals mass of the chandelier times acceleration. Now I know that this is a little bit messy, but we actually can clean it up very, very quickly. One of the first things I want to do is just go ahead and distribute. So we end up with mass of the chandelier times gravity minus mass times acceleration of Robin Hood plus mass of Robin Hood times gravity equals mass of the chandelier times acceleration. Then what can we actually get rid of in here? If we actually look, this is going to simplify very quickly because most of this
isn't it minus mass of Robin Hood times gravity because it's...
Yes, thank you. So let me go ahead and correct that because I distributed wrong. And again, if you guys see any mistakes, please call me out really, really quickly so we don't continue working. I do make mistakes when I'm trying to talk and do math at the same time. We now have a whole bunch of things down here which kind of look ugly, but we can start to rearrange these, and we have numbers. Now, in the problems we're working on, this will actually simplify in a lot of ways. I've tried to make sure that they could simplify. The problems we're doing for the exam, the way that they're going to simplify is I'm going to give you a ratio on masses, for example, or say the masses are the same. If the masses here were the same, what would actually happen?
You could just cancel like all. You could get rid of all of the masses.
You could get rid of all of the masses. Now, this isn't the case here. The case here is they gave us numbers. We can actually plug those numbers in. I'm going to go ahead and do that before rearranging. All right, so we have an equation that says mass of the chandelier, which was 220 kilograms, times 9.81, minus mass of Robin Hood, which was 82 kilograms, times acceleration. The other thing is, this acceleration here of Robin Hood and this acceleration of the chandelier are the same. How do we know that? Because they're connected together. It's one system that is connected together with a rope. This would not be the same if that rope was stretchable. That makes it a very difficult problem. That's a calculus-based problem right there. All right, back to the problem, minus 82 times 9.81.
Wait, you left that acceleration empty. Is that supposed to be empty?
What's that?
The 82 kilograms, isn't that times 9.81?
Where is that at?
Acceleration of Robin Hood. You did 82 times A minus 82. Wait.
It should be there. I think I just put it in, didn't I?
220 times 9.81 minus 82 times 9.81.
No, it should be A. That is actually, this is acceleration. And he is not accelerating at 9.81. This is an unknown. It is not G anymore. That is not 9.81. He's actually going to go slower. He's actually going to be slowing down acceleration. If there was no Robin Hood, the chandelier would fall at 9.81. But because there's a system here, we no longer have 9.81 as the acceleration. We're actually going to solve for it here quickly. Mass of the chandelier on the right-hand side is 220 times A. I'm going to go ahead and give you 3 minutes. We've actually solved this in terms of numerically plugging numbers in. We actually now have a system that's turned into a single variable equation. I want you to actually plug numbers in, grab your calculator, and solve for what's the acceleration in Robin Hood. You guys have until 12:35.
It is 12:35.
I'm sorry, 12:38. Thanks. Glad you guys always got my back.
See, it never seems that bad when you're doing it in class, but then you try to do it by yourself and then you're like, I don't know what physics is.
I get that same feeling.
Because, like, this just makes perfect sense when you set it up like this. Like, okay, I can follow this. But then trying to do it by myself, it's always a disaster.
Y'all get approximately 4.5,
Yeah, I got
Yeah.
4.48.
but it should be 2 sig figs, right?
Yeah. So A equals 4.5.
And yes, Audie, with the 220 kilograms, it should be 2 sig figs.
So then how do you find the tension? Because you can't...
If you're solving for the tension, Ashley, at that point, if you go back to, if you're still looking at the screen,
Mm-hmm.
you would actually go back to one of these equations, either here or here, and you would plug your acceleration that you just got back in.
Okay.
And at this point, you would know all the other components other than tension. So you would have to go back to one of the equations before you replace tension and use it to solve.
So you'd
And on
use,
problem 74, that's how you solve for tension.
so you'd use like T equals the mass of Robin Hood, or MA plus MG.
Mm-hmm.
Okay.
And yeah, to be honest, this one right here would be the easiest one to use. Because you already solved for tension there. So just mass times, and that was with Robin Hood.
Yeah.
So, yeah.
So,
Yeah, that would be the easiest one right there to use.
So we're gonna use the mass of Robin Hood. Yes, because that's
Yep.
that's what that one is.
So yeah, it'd be 82 times the acceleration you got. And what did you say it was? 4.5
4.5.
plus
82 times 9.81.
82 times 9.81.
What did you guys get for acceleration again?
4.5 meters per second squared. How did you know that when you like put the positive and negatives that you could just like switch it for the different objects?
In this case, we were assuming actually a direction. We were assuming a direction in terms of what was going to happen with acceleration. Nabia, to be honest, if you're assuming a direction like this and you ended up with a negative number down here at the end for A, that would mean you assumed wrong. But because we assumed both of these were going in a certain direction, they were attached to one another, we would have actually got an A that was constant for both. So we would have simply ended up with a negative A value.
Okay.
So for the tension, I got 1,173, but ignoring sig figs. What units is that in? Is that in newtons?
That would be in newtons.
So 1,172 newtons. To put it in 2 sig figs, it would be 1,200.
1,200.
Alright.
All right, if you guys would join me on page 8. Or sorry, page 9.
I was like,
Wait. No. Can I go back for a second? Like, what if instead of like, you know how for Robin Hood up is positive, but for the chandelier down is positive? What if you just made both of them like positive for up? You know, would you have been able to get the right answer?
On this one, I would have to actually go back and check. There is a possibility that you would have gotten the right answer. The possibility also there, sometimes if you do that, you end up with an unsolvable problem.
So that's when you should go back and. Okay.
Yeah, that's when you should go back and check directions. Directions here are really, really weird. You would have ended up having you have to have a negative acceleration then, because what ends up happening is you actually would end up with possibly a series of equations which give you an answer that doesn't make sense.
Yeah. If you didn't.
Most likely, Nabiha, you would actually come up with a solvable answer, but when you plugged it in, it just wouldn't make sense.
Okay, yeah. Okay, so just don't do that.
Just don't do it.
Thank you.
There's a reason I'm trying to coach you guys through these. All right, let's do problem number 79. And again, we are on page 9 of 11. Problem number 79 says a box sliding up an incline.
Is it okay if I record this again?
Yep.
Thank you.
Of 15 degrees. With respect to the horizontal, the coefficient of kinetic friction on the box is 0.18. Mu equals 0.180. Mu is a unitless number. It doesn't actually have units. It is force over force. It's comparing two things of the same units together. So mu and the Reynolds number, there's a bunch of these that actually don't have units. It's a direct comparison to two forces. it talks about how big is the force of friction compared to the normal force. And it says the initial speed at the bottom of the incline is 1.5 meters per second. And it asks,
How far does it travel before coming to
how
rest?
far does it travel? Alright, so it's asking for displacement. And the first thing I'm going to do, as always, free body diagram. I'm going to do that right over here. And first thing you can always draw. Gravity acting down. mg. So I got asked you guys last year a bunch of questions. Does it exist in the real world? Yes. Gravity probably is affecting it. Draw on gravity. Second thing, is there a surface? In this case, yes. That means that if there's a surface, we actually have to evaluate for two forces. The first one is normal force. Now, IB is stupid, and they call this the reaction force. I don't call it reaction because what do I always call R?
Resultant.
Resultant. So I hate using R. I'm doing it here to model what you would do on the IB exam. I hate using R. I typically will use normal force, F of n. But again, they have it down in their equations as R, the reaction force. IB is the only one I've ever heard used called the reaction force. Everybody else calls it the normal force. It's normal to the plane of interference. In this case, the plane of interference is the surface.
Will you write it in as Fn?
I'm probably just going to use R for right now, actually.
Okay.
Just because I want to model using your equations in your equation packet, the equations you have.
Fair enough.
Right here, if we have a surface, we also have to look, is there friction? There is, and friction is going to oppose the natural motion of this. And the natural motion, this is moving up. So friction is actually going to be in the downhill direction. This is unusual for us. Usually friction is facing uphill. So there is the force of friction. We now have a free body diagram that has all the forces attached.
What about the initial
There
speed?
there's
Does that
no
not
tensions or anything else. What's that, Ashley?
Does it not matter that there was the initial speed?
It doesn't. The initial speed is not a force.
Oh.
The only thing the initial speed does is actually change the direction of friction compared to what we normally deal with, which is normally friction is pointing up the hill. And actually, if this box came to a stop and then started to either go back down the hill or came to a stop and rested, at that point, that force of friction would actually switch directions. And we would actually have to stop, build a new equation set, and stop all of our stuff there and start over for equations. In this case, we're just going to use this right here. Now, with all of these, we actually have to get them into equations that we understand, which means they have to actually be in a Cartesian coordinate system, 90 degrees from one another. And a lot of people love to actually do the Cartesian coordinates like this. For a hill, though, that actually doesn't make sense. It actually makes sense to do their Cartesian coordinates
Make one of
with the hill. So we're going to make the hill x, and we're going to make the normal y, which means we actually have to break up gravity into components. And this is actually typical, and you guys should be getting used to this by now. So gravity, we're going to break up into two components. We're going to break it up into the hill and down the hill. And this, by geometry, is our 15-degree angle, which makes this one the opposite side, this one the adjacent side, and mg is our hypotenuse. We go back to so, ha, toa.
Wait, why do we know that one is 15? Because the surface is on the other side, like it's...
If we get confused, we can draw a really, really shallow angle that'll help us out, just to kind of check and verify. And if we draw a really, really shallow angle, and there is a geometric proof, I'm not going to go through it just to make sure we have enough time to actually do it. And to be honest, This is the type of thing you could find online very easily. If we have mg and into the hill, we would find that this angle actually matches this.
Okay.
All right, back to the SOHCAHTOA.
Sorry.
You're fine. We have two things. We're going to have normal and into the hill. This is R, which, again, that's the normal force. And this one is actually the adjacent force. So the adjacent component of mg is mg, and adjacent is cosine of the angle. And we know that these have to be equal and opposite. Why do we know that? Because this box, actually, we know just from our own experience that it's not either going to fly off the hill and it's not going to drive into the hill. It's not a plow and it's not an airplane. So we know that everything going directly away and directly into the hill actually has to equal 0. There's no accelerations in that direction. So we can actually say the normal force is equal and opposite, so it's the same thing as mg cosine of theta. And this actually does play an important role. Because when we come down
Shouldn't it
and
be
we
R?
actually, what's that?
Shouldn't it be R?
And I am going to replace it with r in just a second. And actually, I'll just put r equals here. When we look at this component here, that actually creates an acceleration. This box is sliding up the hill and slowing down. This force and this force both act in that direction, and they both act in the same direction. Both of them are going down the hill. Now there's a couple ways I can handle this. Ashley, you're not muted. Pick a direction, up the hill or down the hill. Which one's positive?
Up.
Okay. So Ashley decided for our group that we're going to say this one is a positive direction. Okay? All right. So that means we have two forces that are acting in this direction, and we're going to add them together. The first one, again, is the component down the hill. The sum of the forces down the hill is equal to this component, and that component is negative mg sine of theta. The reason it's negative is because it's pointing in the opposite direction than we said is up. With force of friction, that would also make the force of friction negative. Negative force of friction. And this is going to be, again, I said that this is the most powerful and the most worthless because the sum of the forces is useless. What we're really trying to get to is an equation that uses that. That is the sum of the forces, and we know the sum of the forces is mass times acceleration. We now have a problem. We don't know what the friction is, but we actually do know what one of the relationships are. We know that force of friction is equal to, because this is sliding, they don't use sliding, they use dynamic. So I'll erase that and replace that with a D. The dynamic coefficient of friction times R. This is directly out of your equation packet.
Oh, so is R the normal force?
R is the normal force. Yes, it is.
Oh.
MA equals negative mg sine theta minus mu of dynamic friction times mg cosine theta. We now can actually see something that makes our life much easier. There is a mass, and the only mass that's here is actually the mass of the truck. So it actually cancels out. Please don't tell Miss Williams I said that. And we actually end up with an equation that says acceleration is equal to negative g sine theta minus g times mu dynamic cosine theta. Acceleration is equal to negative g times sine theta minus mu cosine theta. These are all known variables. Equals negative 9.81 times sine 15 degrees. Make sure as soon as you do this in your calculator, you check your calculator to see if it's in degrees or radians. Minus 0.18 cosine of 15 degrees. And again, that's all nothing but numbers. Plug that in and give me an answer in terms of what is the acceleration of our block. You guys have 2 minutes until 12:55 to give me a number.
Did you plug in the value for normal force when you were subtracting all the different like components together?
So Lucy, are you looking at the tablet? This right here is normal force. Do you see what I just circled?
But isn't normal force a y component?
Normal force is the y component, and we actually solved for that. We solved for that up here. So that's this part right here. And we said, because of this, because the normal force has to be the same as the force into the hill, we actually can calculate what that normal force is. So that normal force ends up being the same thing as this component, which we know that that was this over here, the cosine component of gravity.
Thank you.
That's where we get this equation that's underlined in red. And we can take this equation here and we can plug it in for the normal force. And we did that because, like I said, the IB uses R, but this right here is the normal force.
Right, I get how you find normal force. How come you plug it into your equation with all the x values? Like, don't you want an equation for x and an equation for y? Or you just pick all the forces together?
In this, the force of friction actually is related to both. The force of friction is in the x direction, but it's directly related to the force of normal, which is y. So it goes actually between both, and mu is a comparison between them. So the force of friction actually has a component in each. The force of friction itself is 90 degrees to the normal force, and they are related.
So why do you need the normal force if you already have the friction force, which represents
We did not have the friction force. All we had was this.
So what's the
We
equation?
actually needed to have what it was in terms of this equation here.
I
So-
thought mg sine of theta was the friction force.
Mg sine of theta is actually not the friction force. Mg sine of theta actually is this component down the hill. We actually have two things that are pointing down the hill. Gravity, if we were rolling this up the hill with zero friction, it would still come to a stop. Why? Gravity is slowing it down. There's a component of gravity slowing it down. In this case, there's an additional force of friction also helping to slow it down.
So what's the equation for normal force? Is it mg sine theta?
The equation for normal force is mg cosine theta.
Oh.
Quick question.
Yeah.
So normal force is mg cosine theta, but r, somewhere it said it was that it's the same thing, right?
Mhm.
There's
Yeah.
Okay, because you like crossed out the mass when you were like plug something in for r, so I was like, is it just normal force divided by mass? And okay.
Yes, R is actually just normal force.
Okay.
Also, Mr. Peterson,
Yeah.
when you factored out the negative g, isn't it supposed to be sine theta plus mu times cosine instead of minus?
Yes, actually, thank you very much. I appreciate, like I said, when you guys see me make a mistake, please call me out. It should have been plus here. Thank you very much. Because yes, when I factored out a negative g, I should have factored it out of that area too here.
And when you draw the free body diagram, do you have to like put the angle that mg is at?
Yes, it actually is very important here. If this was a steeper hill, it would slow down faster. If it was a
Yeah, but you have to like draw it in the free body diagram.
so yes, it needs to be included in the free body diagram because that does actually, when it comes down to breaking that into components, it does actually matter.
Okay.
Because the thing with the free body diagram is the angle between the the reaction force, the normal force, and the angle between mg is off by 15 degrees. So that actually is important. All right, I do want to finish this up before we actually run out of time. We have about 12 minutes left. What did you guys get? Oh, and thank you very much for speaking up. If you guys would please make sure and run this in a calculator really quickly and find what do you get for acceleration?
Negative 4.24 meters per second squared.
All right, negative 4.24. Can I get a thumbs up for people if they actually ended up with the same thing? Janice, you have that down?
I got a different answer, but I think I made a mistake.
Right, I'm seeing a lot of people with a thumbs up, which means I'm going to assume we have a right answer. Thank you guys very much for showing me that you're working with me. I do appreciate it. So if you jump to slide 10, I went ahead and wrote the acceleration down. Now we weren't quite finished with this, and this is the problem that actually gets us to what we're going to do for the test tomorrow. We solve for the acceleration, and when we're solving for the acceleration, we're going to solve for it theoretically. So, like I said, 1/2 of g or 1/8 of g. And then we're going to actually have to use that to actually put that back into equations. We had a truck on a hill, and we were asking what was the displacement it would go up the hill.
Wait, is this for
That
different
was the initial question. And again, we are on page 10. We solved for the acceleration using a free body diagram. But now we have to use the motion equations using SUVON. And quickly, let's write out SUVON. Displacement, that's actually our question. Initial speed, we had 1.5 meters per second. V, what's our final speed?
0.
0, thank you very much. Acceleration was equal to negative 4.25. And do we need time? No, we don't. So we're going to look for an equation that has this. And if I look through my equations, I will find an equation that says V final squared equals the initial squared plus 2AS. V final, 0 squared equals 1.5 squared plus 2 times negative 4.25 times S.
Oh my
We
lord.
now have an equation.
My mom keeps like opening and closing the door and scaring the living shit out of me every time.
At least your dog is cute.
Huh?
So at least your dog is cute.
Agreed.
So what is negative 4.25 times 2?
find negative. Keep going.
Negative 8.48.
So you guys get negative 8.48.
I did something wrong. Why did I divided by 0? Why are we supposed to put 1.5 squared on the other side?
We don't divide. We actually need to subtract because the mathematical operator between this is actually an addition. So we subtract, and I should have actually written this outside of the brackets because we're going to square first before we subtract. PEMDAS, parentheses first. So we now have an equation. The negatives will cancel of negative 1.5 squared over negative 8.48 is equal to x. The negatives do cancel. We end up with a solution. If you guys would plug that into a calculator really fast, 1.5 times 1.5 over 8.48, what do you guys get? Jay, I haven't heard from you. What did you get?
0.265 meters.
0.265. Did anybody else get the same thing? All right, a bunch of thumbs up, Audie. Good job, buddy. Thank you for volunteering your answer. All right, we have a little bit of time left. I want to just take this time to answer any questions you guys have. Again, I want you to feel free to actually take your microphone and turn it back on and unmute yourself, say hello, and ask any questions you need.
I have no idea what the hell you just did, not gonna lie. You like when you were setting up the equations, I got it. And then you started like after the like force of friction, then I got really confused.
Okay, well, we can do some more practice on this.
Okay.
All right. Is there anybody else?
So in the Robin Hood problem, I'm confused about the tension. Is the tension the same in the whole row?
Yes, Alex. When we're working with tension, and this is a good one because about half the problems tomorrow have tension in them. Actually, most of them have tension in them. When we're dealing with tension, the tension will be the same for all pieces of the row. So if we have 2 points that are attached, so the tension's pulling 2 places, we would have 2T. And if we had another place, those tensions will all be the same. And that's always true. The tension in a rope is always the same on the left as it is on the right, or up as it is down.
Okay.
What's our equation for tension again?
Our equation for tension, Lucy, usually comes directly out of a free body diagram. So we have to build the equation for tension. There usually isn't a standard equation for tension.
Is it
Mr. Peterson, is uncertainty on the test?
Uncertainty is not on the test, Raj. You guys were great about communicating with me. We're going to work on uncertainty here in the next week. So after this test on Wednesday, we're going to actually have a little bit of uncertainty practice on Thursday. I'm going to ask you guys Thursday night to actually graph your results. Everybody should have results for their lab. You guys have had enough time that if you needed to redo it, you could have redone it. And if you need to redo it on Wednesday after the exam, that would be the expectation. So we're going to redo some of the how do we handle uncertainties while we have the lab data in front of us.
You said it's open note, so we can use like any practice stuff we do today.
And of course, Janice, it is open notes.
Are we gonna need to use sig figs for when we answer?
You should always use sig figs on, but I'm not going to pick on it explicitly. You should do it though, because some of the answers will have a boundary conditions. So try your best. If you're outside of the boundary, you don't use the appropriate sig figs, you could end up with getting an answer that's marked wrong. Like if it's supposed to be 12 and you only put in one sig fig and put 10, and I said, for me, I can put boundary conditions that say it needs to be between 11 and 13 for the answer. If you put in 10 with the wrong sig figs, you would be marked wrong.
All right.
Any other questions?
How are the tests gonna work for tomorrow? So are we allowed to do this at any time during the school day tomorrow, or?
Well, Audie, that was the last thing I'm actually gonna talk about. So, if there's no more questions, I'll go ahead and answer that right now. So for tomorrow's